This video will be about the servo tester I made using an STC15W201s microcontroller. This is an 8-pin version of it. I developed it on a 16-pin version. I'll show that later. First I'm going to demonstrate its use. It's being powered by just a little power bank through a switch. It's just a SG90 type servo. I believe this is a metal gear one. This is a pot that adjusts it, so we're approximately the middle. It's pretty responsive. This is a 10K pot. This microcontroller doesn't have an analog to digital converter. It does have a comparator though. So I used the comparator to read the pot by having a voltage reference, and then it charges the pot up and then discharges it through these little capacitors here. They're each 0.1 microfarad, so there's a total of 0.2 microfarad capacitance. So to read the pot, you charge up the capacitor by setting this pin high for an amount of time long enough so that they're fully charged. I'll go into the math in a minute. And then to read the pot, you set this pin that charged them low so it starts discharging. And this other wire here goes to the input of a comparator. And when it changes from a high to a low, or from more voltage to bend the reference to less, you get an output that you can read. If you do that in a loop, you just end up with a counter. So it's just a simple loop counter, and then you can use that and scale it to the output for the microcontroller, for the timer. The timer uses the 16-bit timer 2 in this. This chip has two timers, timer 0 and timer 2. They're both 16-bit. It's in timer 2, which this one uses, only has one mode, 16-bit auto reload. And I'll explain a little more about that in a minute. You can see it works pretty stable. I had a terrible time getting this to work though, and I'll explain that in a minute. Power comes in here. Power to the microcontroller goes through this diode. It's a Schottky diode. I'm not sure how to say that. And this capacitor here helps smooth out the voltages. The power for the servo comes straight from the power source without going through the diode. This seems to give a little separation from the between the digital logic and the comparator mainly, and the servo, which creates a lot of noise and pulls a lot more current than you would think, which makes the voltage fluctuate. Other than that, the circuit is pretty simple. I've got a couple of pins on there just for demonstration purposes. I've got my little scope set up here. It's hooked up to, the probe is hooked up to ground, and the digital signal from the microcontroller that produces the pulse for driving the servos. I'll adjust it with the pot and you can see the output. Here we are at the lowest point. We're set up at 0.5 milliseconds, so we're at about 1.5 divisions, so that's 0.75 or somewhere around that. And then we'll go the other way, go slowly, so you can see it is pretty stable considering the method used to read the pot. And that's at its other end. So we got 1, 2, 3, 4, a little over 4.5. So let's call it 4 times 5 is 2 milliseconds, and so 2.25 milliseconds. That's what I was shooting for. That's close. everything I wanted to show was the separation between the pulses. So let's change this to 2 milliseconds, and there you can see 2 of them. These are the pulses that drive a servo. They're at about a 50 hertz or 20 milliseconds interval. You can still see the pulse width changing. Let's count them, make sure we got what we wanted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, a little over 10, pretty close. Close enough for this. This is a nice little scope, although sometimes it seems to have a mind of its own. Now I'm going to explain some of the trouble I had when I was trying to develop this. I did not develop it on the board you just saw me using before, a little soldered up point-to-point wiring board. I used this little development board I built. This is a work in progress. This is like the second version of it. It has a programming header, a switch for cycling power. It can use either an external source or be powered from the USB port. So on a servo circuit, you definitely want to use external power. The servo goes into these. There's 3 of these little connectors where you have a standard servo setup or other sensors with ground, power, and signal. These 2 signal pins here are connected together. So to hook it up to your microcontroller, you just run it up from that pin over to here. This is an idea I got from watching the Ben Heck video. He did a video on making an A-Tiny board, programmer development like board, and he used physical switches to separate the programming hardware from the microcontroller unit in its final form. That's the way this is. These switches just allow you to select where these pins, in this case these 2 pins, are connected to either it allows you to select where either the pins on the actual chip are connected to either these pins, these little headers here, which are all have commons, or the programming header. So when you got the switch pushed this way, your microcontroller pin, like this pin, is connected to all 3 of these, and then you can use jumpers to come out to whatever you want to. If the switches are set the other way, like this, your microcontroller pin is connected to a programming header, and you can program it with a USB connector or USB converter I've shown in the past. This little switch allows you to select whether you're using power from the USB side or from this connector right here. In this case, we've got it set over to here. The other interesting things about this board, you have power and ground connections, some LEDs. So if you wanted to operate an LED, this little header here, you just jumper it to whichever pin you want to drive the LED. These are switches with pull-up resistors. So you can just do the same thing here, jumper from here to whatever pin you want to connect it to. It has a power LED. The reason I use this is to have a decent quality switch for programming, because you start the programming cycle on this by cycling power. This uses the circuitry right out of the STC datasheet, using the 1N581 diode and 330 ohm resistor in line with these programming pins to try to help separate, well, not separate, it keeps the USB converter from powering the chip even though the power is off. Phantom power, in other words, which would prevent the reset of the chip and get in the way of programming. Now I'll power this up and show you some of the trouble I ran into. You can see this servo is jittering. Over here is the pot for adjusting it. This may be part of my problem too. But jitter goes away right about here. Very interesting. But it's these pulses get longer for driving the servo, which I believe also the servo produces longer internal pulses for driving the motors. When it does that, it starts to jitter. I had a terrible time with this, trying to figure out if it was my program or something else. I finally have come to the conclusion that it's just the board needs bigger wires going to the servo power. Although there's another solution I added on the board I soldered up. I read about it on the somewhere on the internet. I'll show you what that is. That board that we saw before has a 1N5819 diode from the power side, like the positive side of this power goes through a 1N5819 diode and then drives all the digital circuitry. The VCC to the servo just goes straight to the servo, and of course they have common grounds. But this diode hopefully keeps some of the voltage sags from getting through to the microcontroller, the digital stuff, which probably plays havoc with this comparator. That's my assumption. I'm not sure, but that's what I went on. I put the diode in the other board, but when I jumper across it, it doesn't seem to make much difference. So this may or may not be needed. I'm not sure. It may just be that I have much better paths for the servo power supply than I do on this board. But this still does mostly work. If I put that diode in between here and here, it also stops jittering. Or if I just run longer wire, or if I separate wires to the servo power separately and not go through the board, it quits jittering. So it's interesting. I'm not sure if that diode is needed or not. This is a learning process. I'll show some of the way this operates now. The pot that we were adjusting is connected to ground through a 2 microfarad, actually it was 2 0.1 microfarad capacitors in parallel. Port 3 pin charges the capacitors through the pot. So this is the middle terminal on the pot. It charges it up for the math is 10K, 10,000 ohms, 2 microfarad is 2 microfarad. So to get the time constant, 10,000 times 2 microfarad equals 0.002 seconds. And to charge it, we need to charge it for 5 times that length so that it's fully charged. So 5 times 2 milliseconds, I think I said milliseconds, is 10 milliseconds. So that's how long that pin needs to stay high to make sure this is fully charged in the worst case scenario, and this is set it all the way at one end. To read the pot, we turn this to a low, so this starts discharging through the pot. Then the comparator, our comparator input, is hooked up to this pin. When this goes low, we get a change on our comparator. What it's comparing it to is a band gap voltage inside the microcontroller. You can see right over here. This is a diagram of the comparator. You can select a band gap voltage or another pin as its value for this negative pin. So this is what we selected for the negative side. Our positive side is this pin right here, P55. And when they change, it also runs, these are software selectable. I turned all this on trying to get rid of some of the jitter. So all this is selected, maximum delay, and a little filter here. Then it comes down here. We're just polling it. We're not generating any interrupts or putting the output to a pin, which you can do, at least on the 16-pin version. Oh, the other thing is I developed this on the 16-pin version because I didn't have any 4K 8-pin versions. That's why you saw that chip on that board. They're functionally the same, it's just so you have less pins, the 8-pin version, and basically they chopped off the top 8 pins of the chip. All the others are still there, so the comparator output is not on the 8-pin version. I hope that's not too crazy, it's getting too deep into it. So to read this value here, we start discharging the capacitor through this port, through a resistor by grounding this. Then we start examining the comparator output in a loop. And then the loop just keeps a counter, and however many times it goes through the loop, it's how long it took to discharge that. It's pretty simple stuff. The basic stamp used to use a similar technique, but it used just the digital pins on the chip, and it only used one pin. I tried to make that work, but it was not successful. To produce the pulses we need, we're using timer 1, which is a 16-bit timer. I tried doing some work with an A-Tiny. They only have 8-bit timers. A 16-bit timer is much easier to use. You get a much wider range of a delay or whatever you're going for. We use timer 1, or not timer 2. Timer 2, these all should be timer 2 because this chip doesn't have timer 1. I think I'm correct all that. We use timer 2 and it only has one mode, 16-bit auto reload mode. And we're going to use it, and we're going to use an interrupt to generate the clock. The auto reload mode is the important part. Every time the chip rolls over, whether it generates an interrupt or not, it reloads the timer from a hidden register. The register, you can't write to it if the timer is turned off. If the timer is running, that's the register you're writing to when you write to the timer high and timer low registers for this timer. So the way we do this is when it overflows here, we set the pin high and we put a value that's equal to this long pulse in the timer 2, into the timer 2. What that does is writes to the reload value, so it doesn't affect this, it affects this when next time it reloads, so you're always like one behind. So you set the pin high, put this value for this delay in the timer register. Then the next interrupt you get, you set the pin low, and then you put the timer is already starting on this delay, so you write into the timer 2 the value you want for this pulse, the length for that. And these are this is a count up timer, so you got to remember to subtract whatever length you want from 536. The clock source of a timer is the CPU clock, which is, I've been using 12 megahertz divided by 12. That's set by a register. It can either be 12 megahertz, the CPU clock, or the CPU clock divided by 12. I kept writing T1 for some reason. So we get an increment of this timer. When we divide it by 12, we get an increment every 1 microsecond. When it goes from 65,535 to 0 or rolls over, you get an interrupt. That's when these things happen. So this is the part I thought would be hard, but it was the part that was actually easy. I've tried this on an A-Tiny and it's not fun. Here's a little, these pictures help to determine what's going on, I think, better than reading. You got a system clock. We've got it set to divide by 12. Comes in here. We have it set up as a timer. So it's going to time. You could count things on the pin. But we got it set up as a timer. Comes through here. This is the run bit that tells it to run. We're not using any of these interrupts, or we're not using the gate. We are using an interrupt. But that runs this, runs through here. So and here's your counter. They count up. When you write to this register if the timer is running. When you read from this register. If the timer is not running and you write to it, you're writing to these registers. And here's where you get your overflow interrupt after it overflows. You can also enable a clock out, which toggles a pin every time this happens, every time this overflows. That's handy for producing square waves without any software at all, or without any interrupts or anything. You just set up for registers and it'll run, toggling this pin, and it'll auto reload itself. And, I've used that. I may show how to do that in a future video. I believe I'll show a little bit on the program and then we'll call it quits on this. Here we are in Notepad++ with our Servo program open. We just do some defines at the top. The LEDs, it was for testing purposes. The other ones tell where the servo is connected to. The pin that charges up the capacitor, and the pin we're going to examine pot is the one that the comparator plus input is hooked onto. That's what's going to tell us when the capacitor is discharged. There's a couple of bit flags. I'm going to first show the a foreground task, the main function, where we this is going to be what we get from when we read the pot value, and then we have to convert it to something we can use for the servo. These set port modes are some routines that I've done in other videos that just set which mode these the port pins will be in. All of these will be in push-pull mode. I've done videos or mentioned that in videos before. The servo position, this 1500, is in microseconds, so that's the center of the servo position. But we have to subtract it from 65,536 because we got an up-down or an up counter. This is the initial state of the servo line and charging the pot. Initialize the comparator is a function I'll show you in a minute. It just sets some registers. We're going to set those flag bits to their initial states. Here's where we tell it that timer 2, I keep putting timer 1 for some reason, that's supposed to be timer 2, is in the divide by 12 mode. And this is the timer, these two writes here, timer low 2 and timer high 2, is the value for a 19 millisecond delay, or timer interval, I guess you would call it. You're going to enable the interrupt and then start it running. This is the global interrupt enable right here. Right down here is the main part of our loop, just a forever loop. The reason we have to wait for an OK to change, we don't want to write a new servo position because it's two bytes. And if we're in the middle of writing a servo position with 2 bytes and the interrupt occurs in between the 2 writes, you're going to have bad things happen. So the OK to change flag is set in the interrupt routine right at the start of the 20 millisecond interval. That way we have plenty of time to read the pot and write a new value before the interrupt is called again. Pot value is read pot. That read pot is a routine up here I'll show in a minute. Returns an unsigned character. No, it returns an unsigned integer, 16-bit integer. Here's where we convert it to something we're going to use for our servo position. This map function right here, that's straight out of the Arduino documentation. Right here it is, map. And here, down here, I just copy or copy and pasted this right here. That's all the code. It uses long variables, which is what's eating up all the memory in our little 1K chip. So we it maps the pot value we read up here between 0 and 1500. 0 and 1750 is what I got on from when I did the read pot routine. I have another program, and I'll show it in a minute, that shows how to scale a pot, and the numbers we get from it are these 0 and 1750. Actually, I just leave the 0 alone. The 1750 though is the number we need to get by just examining our actual circuit, or reading the values that our actual hardware has, the resistor and the pot. This is where we set the new servo position. We have to remember to subtract it from 65536. That hung me up more than once because it's an up counter. The 775 is just a base value for our servo pulse. So even if we have it get a 0 out of this into this conversion value, we'll still have a 775 microsecond pulse, and that's the low limit of the servo pulse. Up here is the initialize comparator routine. It just tells it I just set these 0 to start with, and then started ORing or adding in things to set the bits. This output enable doesn't matter on the 8-pin part, but on the 16-pin part, it'll actually set port 1, 2 to the value of the comparators coming out, or the value you're getting out of a comparator. So it'll be 1 or 0 depending on if what you're comparing to is higher or lower than the reference. And you can invert that. This right here, choose BGV as a negative polar comparator. There's very little mention of this in the data sheet about what BGV is. I think it's like 1.25 volts, but I'm not sure. That's just from looking at other microcontrollers. That gives us an internal reference, and we don't have to provide a reference on one of the other pins. We're going to enable that little filter and make this delay for debounce delay as long as possible. And this is where the comparator actually gets turned on. There's that map function I copied straight from the Arduino reference. Read pot. This is way simpler than you would think. It just sets a time integer to 0, unsigned integer. Pot charge equals 0, brings that line low to start discharging the pot, and then these right here are the 2 bits you have to examine to determine if the comparator has switched states. So as long as they're not changed, we'll increment a time variable. After they change, all we're going to do is start charging the cap again and then return the time variable what we got here. So all we're doing here is just incrementing a variable while we wait for that state to change. And then we go back to our charging the pot, so it has plenty of time to charge up before we use it again. Up here is the set port mode. I've showed that in other videos. It just sets the mode of the ports to, in this case we're just using the push-pull mode. Here's the interrupt routine. It's pretty simple too. We're going to toggle this flag variable every time we go through, and then if it's a flag variable set, we're going to tell it servo equals 1, set the servo line high. Make sure that the foreground task doesn't change anything until it's safe by keeping this as a 0, and then we write our timer values for the 19 millisecond reload. See, this is the 1. This is our actual servo pulse that we're starting here. But the next time this interrupt happens, this will be loaded into the timer. That's our 19 millisecond or 20 millisecond time for the between servo pulses. If the flag is 0, we're going to say set the servo line to 0, drop it down to 0, make it low. Now we're ready for the foreground task to do its thing. So we signal that by OK change equals 1. And we write the actual servo position into the timer. So that'll, next time there's an interrupt, that's what will be reloaded into it. It's actually pretty simple, I thought. And that's the walkthrough of the code. Now I'm going to show how we actually get those values we needed to scale the servo position according to the value we got from the read pot routine. And that is this read pot C program. This uses a lot of our routines. I don't believe this will fit in 1K. I didn't even look. So you need the 4K chip to do this. This uses a lot of our routines that I've showed before for just software serial routines for sending out numbers and even characters. Down here is the same read pot we got in our other program. And this is a conversion routine I tried, but I give up on it. This is not used. Here's our map function, setting up the comparator down here. And here's the main function. We're just going to set up some stuff. The same as our other program did. Start charging the pot, initialize the comparators, print some stuff so we know what things working at all. And then down here, we're going to delay a second. Send some line feeds, send the port value out, that would just debugging stuff. Then we're going to do a read pot, send another line feed, and we're going to send the value we got out of the pot at the serial port. Then we're going to do the mapping thing. Call our mapping function. Then we're going to print out the value we got from that so we can tell what's going on. I'm going to load that into the microcontroller and show and demonstrate it. So let's go into here, open code file, go back to read pot. Got our clock set at 12 megahertz for this to all work. Now I'm going to turn on the camera for the back to this. We need to set our switches in the program mode, these two switches, so that we can program it. Hit download program, cycle power, and it's sending it over. And it's just that easy. We need to leave our program switches in programming because we're going to use those lines to get the serial data out of it. Clear buffer. Make sure we're in text mode. Open COM. And here's the port value, the initial value read from the pot, and the converted value. So let's do some adjusting. That's maximum turned all the way up. And here we are all the way down. So it looks like our range is 6 to 1760 or 1728 or something like that. You can see it's actually pretty stable. It's amazing. And the converted value, so 1726 gets converted to 1479. If you get you have to use this routine to calibrate the servo tester. You can just go into your program and start playing with this number mainly is the one you want to adjust. So let's say we set it to, let's just set it to 2000 and see what happens. Get down here and find the compile. I've got a couple of unused variables. That's all those warnings are about. Let's go on here to kill this. Open the code file. You don't have to reload it. I just did. Go back up and open our COM port up again. Clear it and open it up. So we've made our adjustments. We should see some different numbers. See, now at max it's only going to 1287. So you can the bottom end didn't change. Those are, the map function is an integer function, so it's not perfect. But it was chewing up enough memory as it was. I sure didn't want to do it in a float. But you take, once you get this to where you're reading between, the second number is reading between 0 and 1500 or pretty close. And you can take those numbers and use them for your Servo pot program. I hope that made sense. I think I'll call it quits on this video. Thanks for watching.